Alright, hi everybody. So what we're doing today is we are using a model of thermodynamics and the ideal gas law in order to explain this phenomena that I've been noticing every single time I cook rice. I've been doing some Googling and I kind of figured out why this is happening, but I kind of want to explore this idea and think about what's going on. I don't know if you've ever cooked some rice and had this happen to you. I Googled it and they kind of just told me the solution to how to make it not happen, and it seems pretty obvious and kind of like I should have known that or done that, but it's okay, we'll get to it. But so what we're doing is we're going to watch this quick little video I made about myself cooking rice, quick gas law review, then I have some practice Google form questions, and then kind of a more free response question style question. So this again is going to be split up between the 2 days. So maybe today if you just want to watch this video, and then on Friday you want to go ahead and do these practice questions, totally good. Split it up however you want, but I kind of like doing this where I give you 2 things, 2 days worth, and then you kind of get to split it up however you want. Makes it easier for me, and hopefully makes it easier for you, kind of knowing where we're heading. I don't know. But so here's this video. So, well, not here, but so you don't have to be right, but what I want you to do is kind of make this prediction and think about why this is happening.
Bubbly. Got ourselves a bubbly boy.
I hate that I said that so much. I don't know why I said that. It's awful. It's awful. God will hear my shame of me saying it.
Bubbly. Got ourselves a bubbly boy.
I said that because I tried it with water.
Come on, keep on bubbling. I'm just gonna keep on filming this because I don't want to miss it. Oh, moved a little bit. Oh. Here it is popping off. Oh, we got some. It's rattling. That may be all we get. It's probably dangerous. Oh, it's popping out all over the side.
So yeah, whatever, you get the idea. But so what I care about, yeah, sure, it's bubbling, but what I care about is this idea that it was kind of rattling. That lid was moving. This lid went from not moving at all to having a little bit of motion. It went from 0 velocity to some velocity. So what I want you to do really quick is just make a quick little prediction. If you want to just think it to yourself, go for it. If you want to write it on a sheet of paper and then burn it, and then I'll get this, I don't know, whatever. Don't burn paper, I don't know, whatever. Make some sort of prediction, think about what's happening. So yeah. And then let's kind of start with what we can observe. One thing that we can say when we're making these observations is, I kind of just said it, but the pot lid is moving. It went from being at rest to then moving around a little bit. So we can say we went from 0 velocity to some velocity. It wasn't sustained, but it definitely didn't move. So we can say there has to be a presence of a force. This idea that in order to accelerate an object, we need a force. We need forces to accelerate objects. So we have to say, hey, there must be a presence of a force, but what's causing this? And also this idea that this force, sure, we have the force that's moving the pot lid, but we can think about really this force is happening over the whole area of the pot lid. It was kind of happening all over. Sometimes when we think about forces, we can just think about one force. We can see it happening. We can see this contact and this interaction between two objects. Here we couldn't really see it. We could see, yeah, the lid was moving, but we couldn't really see what was causing that force. So this force was happening over the whole area of the lid. We've talked before about how pressure is force divided by area. So instead of thinking about it as a force, maybe we can say there's this pressure over the whole area of the lid. And pressure and force are kind of interchangeable. We can think about them in similar ways. Only difference is that this pressure is all of the forces happening over some area. So we're thinking about the area of the lid. So we can say something is increasing this pressure, something is causing this force, this pressure. And what we want to do is we're kind of thinking, well, we can't see it. We couldn't see that happening. So let's think about what's happening at the microscopic level, because if we can't see it, maybe it's something that's happening outside the range, outside the scope of what we can see with our eyes. So what we want to do first in order to look at the microscopic level is zoom out and look at the macroscopic level, like you do. So we want to think kind of about a situation that we're used to from back in our previous physics learning. So whether it was physics 1 or chem phys, whatever we learned physics before, we talked about this idea of momentum. So let's think about a ball that is heading towards a wall with some velocity of v. And what we're going to say is that this ball, it collides with the wall and it bounces off. Maybe it's a bouncy ball. I don't know why I looked over here like I would have had a bouncy ball lying around. I don't have a bouncy ball. I don't even think I have bouncy balls at school, but whatever. So this ball, it bounces off the wall, and now it moves away with the speed of, or a velocity, not a speed, a velocity of negative v. And we say, well, this underwent a change in velocity, and we know that all objects have, or this object, this ball has mass, so the mass stayed the same, the velocity changed. This object, it had a change in momentum. The momentum of the object changed. The velocity changed. It went from positive v to negative v. That was a change. And from our previous physics learning, we know that in order to change the velocity or change the momentum of an object, we need a force to do that. So we have a change in momentum, and kind of based on what we talked about before when we did physics learning, so back in our previous learning, we talked about in order to change the momentum of an object, you need an impulse, or maybe we just called it a change in momentum. But this impulse is really saying, hey, we have some sort of force applied to our object over some amount of time. If we're looking at this ball, for example, the ball is going from being a nice ball shape to compressing, so that force is happening throughout that compression through some amount of time. So this force, it's happening over some amount of time in order to change the momentum of the ball. But then what we can think about is saying, hey, like there is this force acting on the ball by the wall. And then based on our Newton's third law, there has to be, if there's a force on the ball by the wall, there has to be a force on the wall by the ball. So when we have these objects colliding with the surface, there's some sort of force from our object that's moving and the wall. There's this force, there's this interaction based on Newton's third law. So then what we can do is we don't have to know this equation, we don't have to use it, but if we kind of want to extrapolate this a little bit, we can say, well, we can look at this equation and say, hey, we're dealing with a force, and soon we're going to look at the microscopic scale. That's the next slide. But if we are looking at the microscopic scale, again, let's focus in on pressure. We can say pressure is force divided by area. We said the change in momentum of our object is equal to the force times the change in time, so how much time that's going on for. Then we can kind of rewrite this as solving it for force, change in momentum over change in time. And then we can say, well, we're changing our momentum by changing the velocity, not the mass. So our change in momentum is m times delta v divided by delta t. And then we can sub in that equation for force and say, oh, well, our pressure is based on the mass of our object, the change in velocity of our object, the area, and then how much time this collision is happening for. So that's kind of a mathematical way for us to think about how we can change the pressure of our object, the pressure colliding the pressure within our container. So we're going to talk about kind of more conceptually, but if you want a nice little math explanation, this is a great way to do it, thinking about, hey, if we want to change the pressure, these variables can't change. So, like I just said, let's look at the microscopic scale. Let's talk about microscopically, let's zoom in. We're kind of predicting with this rice situation, it's happening at a microscopic level. So what we can say is, at the microscopic level, the same exact thing is happening with each gas, each little particle, each little molecule of gas that's in our container. The particles we talked about before when we talked about fluids and when we talked about thermodynamics a little bit ago. We're saying every object is made up of a bunch of particles that are just moving around. And if we have a gas, those gases are allowed to freely move. They can move anywhere within our container. And while they're moving around, these particles each have their own velocity. They're colliding with the container. They're colliding with each other. If it's an ideal gas, we're saying they're not going to collide with each other. But we can say, okay, yeah, real life, they're probably maybe colliding with each other at some points. But really the main thing we want to think about is they're colliding with the wall. The same idea with the ball colliding with the wall is happening millions of times with these little particles. And that's supplying, just like we saw before, a force over that area. So because we have lots of these forces, we can think about these forces over the whole area, or in other words, we can say these particles, by just moving around within our container, they are supplying a pressure to that container. they're supplying a force all over this area of our container through these collisions, through having this change in momentum when they collide with the side of the container. So then if we're thinking about, well, we had an increase in pressure when we were looking at this situation with me cooking rice. We saw an increase in pressure. We saw that we had this force. So here are kind of the things that could cause that if we're thinking about this microscopic level. So if we want to change the pressure, increase the pressure that's acting on our wall, acting in our container, there's a few things we can do. We can say, well, if we're thinking about these collisions, if you had a ball that you were holding, if you threw it faster, you know that there would be more force. If you take any object and you throw it lightly at the wall, and then you throw it really quickly at the wall, you know that there's more force associated with that. It takes more force to change this object's momentum. So we can say, okay, well, if our particles have a larger velocity, then there's going to be this larger momentum change associated with it, so a larger force. But so if they have a greater velocity, there's going to be more pressure. There's going to be more force over that area. And we can say that we can do that. We talked about it last time, that the temperature of our object is really just the average kinetic energy of our particles. So the temperature of our gas is just the average kinetic energy, which is based on the velocity. This is telling us if we increase the temperature, we're increasing the average kinetic energy, which means we're increasing the velocity. So if we change the temperature, if we increase the temperature, we're going to have more pressure because we're going to have more collisions, and these collisions will be more energetic, I guess we could think about. They could be supplying more force because they're a lot quicker. So they're colliding more often because they're moving faster, and they're hitting with more force, which means they need more force to change their momentum. They're moving faster. We can also just have more collisions by having more particles. If we have more collisions by introducing more particles, we're changing the amount of particles, we would have collisions more often. It may not change how much force is required, but by doing it over and over and over and again, we're getting more force because we're doing it more often. So if you just kind of have yourself hitting your hand like this, you're like, oh, well, that's not that many. But if you say, hey, 17 of my closest friends, let's all, not now though, not during this time of social distancing, don't do it now, but later when this is over, get 17 of your closest friends and say, hey, hit my hand. You would feel more force, you'd feel more pressure because you'd have more collisions. And then the last one, we could also decrease the volume so there's less space for our particles to be bouncing around so that we increase the likelihood that our objects will collide with the wall. If we decrease our volume, there's more of a chance that our particles will collide. So what we can do is summarize it into this one equation that we're very used to, this ideal gas law, this PV equals nRT, PIV-NERT, whatever you want to call it. And then really quickly, we're given two of these equations on the equation sheet. It's kind of written just like this. This is a screenshot of it. So we have this one where we have this little n times r times t, and we have this other one where we have this big N times kb times t. And really the only difference is this little n stands for the number of moles of gas, so how many moles do you have, and we're going to use that when we're dealing with a lot of particles. So we know that 1 mole from chemistry is equal to 6.022 times 10 to the 23rd particles, that Avogadro's number. So if we have a lot of particles, then we're just going to want to say, I don't want to count all those, let's count how many moles we have. And then if we're dealing with a smaller amount of particles, we're going to use this capital N equation, where we're thinking about just like, hey, how many particles do we have? That N just stands for the number of particles. You'd be like, oh, I got 10 particles. And it's like, oh, great, that's a very countable amount. If we have 10 moles and we have 10 times 6.022 times 10 to the 23rd, that's a lot. So we wouldn't want to write out 6.0, or I guess if it was 10 moles, we'd have 6.022 times 10 to the 24th. We don't want to think about that. We want to just say, oh, 10 moles, whatever. So just kind of, that's helping us think about our scale. But so what we can say is really quickly, if we want to think about this gas law, sometimes the College Board or AP is going to use some specific terminology when they're asking us about the gas laws. So if one of our variables in this gas law changes, other variables are going to change to accommodate that shift. We have to have this equality, this PV equals nRT. If one of these variables changes, then our other variables are going to change. And this is just a quick little thing. They went over this in like the AP video that they've been making. And I was like, oh, I didn't even think about that. That's a good thing to talk about. So AP that's going to use some certain terminology. So if they say the term sealed container, that tells us that N is constant. The number of moles are constant. It's sealed. The particles are not leaving or entering our container. That's just kind of their terminology. If they say something is isothermal or constant temperature, that means that in this equation, T is going to be constant. Our temperature is not going to be changing. If they say something is a rigid container or a container that does not change shape, that tells us that the volume of that container is constant. We're not changing the volume. Other factors in this equation are going to have to change. And then if it says isobaric, or if they show us something where we have some constant amount of masses sitting on top of our container, then that's going to be a situation that we're at a constant pressure. We have this constant push down on our gas. And then this R is just a constant. It's never going to change, so we don't have to worry about that thing changing. And what we really boil down to when we're using this gas law is this idea that PV, or we'll kind of see this too. This is a little bit of a tease for later. But so eventually we're going to get back into looking at thermodynamic systems, and that really involves changes to our system. And when we're doing these changes to our system, we have to keep this equality that the PV over nRT has to equal PV over nRT. So that's just kind of a quick little tease, but that's going to show up later. And then the last little thing that we're going to talk about in order to think about this rice situation is using the gas laws and the graphs that are associated with them. So we have a lot of variables here that we can think about and change. So we have a lot of variables that we can graph. So if there's, I'm just gonna present us with some situations, like what graph would show up with that, and then what is the relationship. So if we're saying, hey, we have this gas, and this gas is changing the temperature, and it's within this sealed, rigid container. So if we had a situation like that, we'd be like, okay, well, the temperature's changing, so I know that my temperature is changing. A sealed container, we said, has a constant amount of moles, so this N is going to be constant, and rigid means that our volume is constant. So if we're looking at using this gas law and creating a graph, we could say, oh, well, V is constant, N is constant, R is constant, and kind of move these around so I can get this like relationship between temperature and the thing that's going to be changing. So I can say, oh, well, I've kind of moved this over, so I have NR over V is my slope, and we say that this P is directly related to temperature. Our pressure and temperature are directly related to each other. And the slope is going to be the moles R over V. So we have this relationship where if I increase the pressure, the temperature increases. Or if I increase the temperature, the pressure is going to increase. One quick little thing about this graph is thinking about this this temperature of 0 or 0 kelvins. So what's happening there is we see, oh, well, we have this 0 pressure. So we think about pressure as these particles colliding with the container. So 0 kelvins, or 0 on our temperature scale, is just going to be absolute 0. This temperature where the particles, they completely stop moving. And if these particles stop moving, then they can no longer exert a pressure because they're not moving. So that's kind of a unique situation. I don't know how close they've gotten to absolute 0, but I know it's like very close. Every once in a while you'll hear like, oh, well, now we're at 0.00001 kelvins or something crazy. But so they're trying to approach this theoretical value of absolute 0, which is a cool little scientific endeavor. But yeah, so that just kind of tells us, hey, 0 temperature, 0 pressure. The next one we can look at is for a situation where we're saying, oh, well, the volume is changing of a sealed container, and it's happening isothermically. So if we look isothermically, we said, oh, well, that's a situation where temperature is constant. So really what we can do is look at our PV equals nRT, identify that N, R, and T are going to be constant because we're sealed, R is constant, and it's isothermal. And then we can set up and say, well, I can relate P to 1 over the volume, and I have this direct relationship between P and 1 over volume. Or I can say I have this inverse relationship between pressure and volume. But if I'm looking at this situation, this is something that's going to show up a little bit later when we're looking at these processes. How would we know that this is isothermal? So how could we use this? Well, what we could say is, well, we just identified that if we're dealing with an isothermal situation, N, R, and T have to be constant. This temperature is constant. We're dealing with sealed containers, and R is constant. You can say PV equals nRT, but that has to ring true every single time. This PV always has to equal nRT. So I can say P1 V1 is going to equal P2 V2. NEP and NEV that create that nRT has to equal NEP and NEV that is also equal to that nRT. So then I can kind of skip that middle step and say P1 V1 is equal to P2 V2. So that's how we can identify if we have this constant temperature, this isotherm. And then what we can look at here is kind of a question about that. Which two processes start and end at the same temperature? So really quickly, give this a quick look. You don't have to turn anything in with this, but I want you looking at it and trying it out. But what we can say is try it out, yeah, and then I'll go over it. But so we want to look at the start and the end. So we're starting at this dot over here, and we're saying, hey, what temperature do we start at, and then what do we end at? And we just said we can find kind of this starting temperature. The temperature will be N times R times the T is equal to P times V, but N and R are going to be constant, so we can just kind of say, hey, where will P and V equal each other? Kind of like what we just had right here. Where will PV equal PV? So we can look and say, well, the starting thing starts at P naught and V naught. So which ones end at P naught, V naught? Well, if we look at A, it goes up to a pressure of 2 P naught. Because the pressure increases, the volume is going to decrease, and that goes down to 1/2 V naught. You say, oh, 2 P naught times 1/2 V naught is equal to just P naught V naught. And do the same thing. This gives us 6/2, so 3 P naught V naught. This one gives us 1/2 P naught V naught. And then this one gives us 1/3 times 3 P naught V naught is equal to just P naught V naught. So it looks like A and C are going to start and end at the same temperature based on that equation. All right, and then another situation, graph for changing the temperature of a sealed container at a constant pressure. So if we are changing the temperature, this particle is getting faster, and then the volume of them is going to increase. They're able to kind of push on our container and change the volume of it. So in this case, we can say, well, P, N, and R are going to be constant. So then we can kind of set this up and say V is directly related to this temperature. So again, we have this relationship at 0T. We have no volume because these particles stopped moving. And yeah, if we increase the temperature, these particles are moving quicker and they're able to expand. Really quickly, let me go back to these because I didn't really talk about that. But I guess this one I did. If the particles are moving faster, they're able to push out more. They're able to move at this higher velocity, so they're able to push more and exert a greater pressure. With this one, if our volume is decreasing, or our volume is increasing, then we're kind of increasing that space, and our particles won't be able to collide as often, so that pressure will go down. And then with the last one, if we wanted to graph the changing number of moles in a rigid container at a constant temperature, we're saying, hey, if we increase more moles, if we put more in there, then there will be more collisions. We'll have more pressure, and then we can have this P is directly related to N by manipulating our equation. I'm skipping this, I didn't like it. All right, so now what we can do is kind of revisit that situation where we're looking at the rice video. So I don't specifically have an answer for this, but we can make a prediction. We can say, well, what we saw was this increase in pressure. We can use this new or old, super old, ideal gas law equation and say P is equal to nRT divided by a volume. So we can just divide the volume. So what we can say in this is, well, in our situation, V was staying constant. We had this sealed container. It wasn't increasing the lid, like it wasn't just like growing and going off it and keeping all the particles in there. We had this sealed situation. So we again said pressure went up. R is constant. And if we're thinking about this, well, T definitely changed it. T definitely had an influence on the pressure here. The temperature of the particles, I had it on a flame, so the air was moving quicker. So I had this increase in the temperature. And then I also had, based on my Googling, an increase in the number of moles. This is actually a weird situation, but apparently this rice has starch on it, and then when you boil it, it is releasing this gas. And what every situation, what every website told me was just like, yeah, that happens. Are you not washing your rice before you cook it? And I'm like, no, I'm not washing it because I'm putting it in water. But apparently you're supposed to wash it, and then you wash that starch off, which will no longer create this gas, which will increase the number of moles of gas inside of that container, and then you won't have a problem because you're not getting that starch anymore because it's washed off, so that starch is no longer releasing that gas that is kind of increasing the pressure of our container. So we have that increase in N, this increase in T, which results in an increased pressure, an increased push in our container. And that's that. Yeah, so this is a nice little breaking point for the first day, and then if you want to try the practice questions now or later, go for it. But yeah, hopefully that was quick and interesting.